All right, welcome back. We're going to finish up these slides today and then start some new ones in theory. And this is a fun topic now. Really, I should be saying CSCI everywhere, shouldn't I? Because that's what we use at this college. Okay, CSCI now in finance. We're going to talk about cryptocurrency. And I'm very happy about the green background because I just used these colors for this theme in order. And green was the one that just appears right now if I follow the order. So I'm very happy about that. All right, so let's talk Bitcoin because that's the major cryptocurrency, right? So Bitcoin is the most popular one, and I am not going to teach you how to make your own Bitcoin. You'll have to maybe come to office hours for that, but I'll be giving you an idea of what it's doing if you're not familiar with it at a very high level. Okay, so I guess we should first talk about what in the world cryptocurrency even is. It is just a type of money that is completely electronic. It's broken up into little denominations, like you can think of it as virtual coins of different sizes. Some are very tiny, some are large, and each of these all has an amount associated with it, like an amount of Bitcoin, just like we have dollars and cents, and we have $20 bills and $50 bills and $100 bills, things like that, and all the way down to pennies, right? So, yeah, a cryptocurrency is just that virtually. That's the idea. And something that's really nice about Bitcoin in particular is that it's using encryption, these things that we've talked about before, keys, to make sure that nobody knows who has what. Everybody has an account number, but nobody can track, really, who owns that account until they start to, like, cash out into, like, currency that exists in the world. Like, if you want to trade your Bitcoins in for dollars, then somebody's going to know who you are. But until then, nobody really knows who owns what. Okay? So it's kind of secretive and cool. It was created in 2009 by a person called Satoshi Nakamoto, and this is not somebody's real name. So this is a pseudonym, and we have no clue who this person really is. Okay, which makes it an even more fun story to tell. So this person racked up a bunch of Bitcoin at the very beginning just to get it started, and has never touched that account. So that's very interesting and exciting, and this person must really care about the future of cryptocurrency. And yeah, so cryptocurrencies, because we have all this encryption going on, they're hard to track because you can just electronically send, like, here's your wallet. They call them wallets. And here's somebody else's wallet. It's very, very easy for you to send Bitcoin using the Bitcoin network. Like, you give this one to that person, and like I said, nobody knows whose account is what. If you stick with Bitcoin, like, you don't cash out, it's very, very hard to track the fact that you're exchanging money with someone else. And obviously most governments want to tax you when you gain income, right? And Bitcoin is another type of income, right? So lots of legal issues behind this concept, and it's just a super exciting one. It's pretty recent, right? 2009, and Bitcoins kind of started this virtual currency craze, this cryptocurrency craze, and a bunch of different kinds of coins, which people like to call as one. They call them altcoins, like alternative versions of Bitcoin, I guess. They have been created, but nobody has become as popular as Bitcoin. Some people have tried, they've gotten close, but not quite. Okay? So how in the world does Bitcoin even work? It's electronic, like we're sending virtual coins to people. What is really going on behind the scenes? So the idea is it's a peer-to-peer network, just like people sharing their illegally downloaded music. There's a bunch of computers that are working together. Okay, so you got a computer over here, a computer over here. These are just across the network. They can be in different countries. They're all talking to each other, and they know what's going on. Okay, and everybody who has an account on the Bitcoin network, they don't have to have their computer on and connected to it. They can use a website that does that. But every user's account, maybe here's the user on their laptop. Their account is hosted on this computer, maybe. Everybody's account has a public key. Okay, that's your account number, in fact. So you got a bunch of like ones and zeros that represent your account number, and then everybody on the network knows that, okay, yes, this account has so much money. Okay, they all have that replicated. That's the idea. They all know your account balance, which is weird to think about. That's not a normal bank kind of thing. But your public key is your account number, and if you want to use your account to spend money, you have to unlock it with a private key. Okay, so it's, again, this kind of two-factor authentication, in a sense, using public and private keys. And the reason everybody agrees, the reason Bitcoin works, is that everybody shares a very large file. Okay, it's called the blockchain. Maybe you heard of that buzzword before. And that, the blockchain itself, records every single transaction that has ever taken place. Okay, so if I make some space for myself, we have this lovely little scroll of a concept. Like here's the little scroll that is the blockchain, right? It's just a really long piece of paper you can think of, and it has all of the transactions that have ever happened across Bitcoin. Okay, so like the very first transaction was, I don't know, account A gave 5 Bitcoins to account B. Okay, and then so on and so forth until like account Z gave 2.25 Bitcoins to account F. Okay, and this goes on forever. Obviously, it's going to keep getting longer as time goes on. And this is how everybody knows which account has how much. Okay? It's this thing called the blockchain. And so I'll use a rainbow to signify that. The magical blockchain. It's beautiful. Okay. So, yeah, the blockchain is kind of the key here. Everybody has a copy of it that's on this Bitcoin network, and they are all trying to agree on what's going on. Okay, so whenever somebody spends their Bitcoins, like maybe they tell this computer on the network saying, okay, I'm giving some Bitcoins to somebody else, this person will write to their blockchain and then send a copy of that transaction to everybody. And they have to agree, okay? They all have to agree. Okay? Because things could go wrong otherwise. Okay? If you are a malicious user, you could totally be like, okay, yeah, here's my computer connected to the Bitcoin peer-to-peer network. I'm just going to take my account, my Lawton's L account. I'm just going to give myself, I don't know, 1,000 Bitcoin from account A. And I'm going to write that to my blockchain. And the issue is, everybody else is going to think you're insane. Okay? Everybody else on the network is going to be like, no, that wasn't real. This did not actually happen. We don't agree. Okay? So there's a way to achieve consensus, which is way beyond the scope of this class. But people understand that, or these computers understand that some transactions are not real. They know the difference. Okay? There is a majority rule thing going on here. So maybe you think that this should be written to the blockchain, but no, the public key, private keys don't match up. The computers don't agree. Okay? So the idea is that 50% of the computers on the Bitcoin network, so there are a ton, many more than this, of course, they have to agree in order for a transaction to go through. That is the idea. A majority rules. Okay? And this could be a problem. It has not been a problem yet for Bitcoin, but it can pose a serious threat because all you need, maybe you're like a government or something and you have the money and the power, you just need to buy a ton of computers and put them on the Bitcoin network, right? If you can get 50.000000001, there's a 1 somewhere, % of computers on the Bitcoin network, then you can change the blockchain to say whatever you want. Okay? So that would make Bitcoin useless, and so their strength is in numbers, and that's why all these altcoins haven't really taken off, because there have been attacks on them that have been successful, these majority attacks. Okay, so that's why people tend to stick with Bitcoin, because there are many more machines connected to this network. Okay, so that is the consensus of Bitcoin in a nutshell. It's very interesting. And so that's how Bitcoin works. This makes sense, hopefully. And now you know all you need to know to like make decisions about, hey, should I buy Bitcoin? But there's another side of the story. There is, we've got all these computers on the network, and it costs energy to like, to run them, to do all these transactions, to save all this blockchain information in space. Like, this is a large energy bill for this computer. What is their motivation to stay on this network, you may ask? And now we have the answer. That's called mining. Mining is the reason that these computers stay on the network and try to achieve consensus and keep copies of the blockchain. So as an incentive to like put yourself out there, make it so that it's hard to do these greater than 50% majority attacks, to buy a bunch of storage and copy the blockchain onto your machine, there is a lottery, in a sense, that happens every few transactions in the Bitcoin network. Okay? There is a lucky participant that is keeping track of like this consensus stuff, and that lucky participant gets some Bitcoin each time they successfully add something to the blockchain. Okay? That lucky participant gets some Bitcoin generated out of thin air, and that's why we call it mining. It's like there is a certain amount of work that a computer has to do that is computationally difficult, and one lucky computer, like the question that mining usually asks is like, generate some number such that it starts with 15 zeros, and the rest are random, okay? And they generate these numbers in a very special way that makes it hard to have a bunch of zeros at the start. That's the idea. So whoever comes up with this, whoever solves the puzzle fast enough, gets these Bitcoin, okay? And this is essentially how you're printing money in the Bitcoin world, okay? So it's like you're harvesting the natural resources of the virtual world. And one day, the Bitcoin supply for these transactions, these mining rewards, they will taper off. So they've already started. So at the very beginning, it gave you a lot of Bitcoin to just write to your blockchain and share it with the world. And that's all going to start going down and down and down and down until one day there is no longer any incentive in this manner. There's no Bitcoin to get out of the network anymore. The one way that you can still make money by putting your computer on the network, this is going to be like 100 years in the future or something, is to still save all these things. You also have transaction fees. Okay, that's the other way. The other way to make money, there are small transaction fees that get paid. Okay, that's the idea. Oops. And that's Bitcoin in a nutshell, I guess. So I guess we should talk about, is this okay at all? The current price of one Bitcoin is, as of like half a month ago, over $10,000. And that is insane, right? So is this okay? Let's talk about why some people don't like the idea of Bitcoin. I've talked about governments not liking it because they want to tax you, but it goes a bit farther than that. So the first uses of Bitcoin, technically the first transaction using Bitcoin that is recorded is very wholesome. Somebody bought a pizza. But the first real uses of Bitcoin were on black markets, to buy drugs, to do illegal things. Okay? And the reason that that's so nice for those black markets is because these governments, they can't track ownership. They can't track the way that you spend Bitcoin. So it's hard to get somebody who is selling drugs, for example, because you can't really track these fees, these payments. So that's one side of the coin. So bad things. You could do very bad things with Bitcoin. And that is sad. The other idea is on a consumer level, all of these Bitcoin, altcoin things, all this cryptocurrency, the exchange rate, sure, it's high right now. It has no real guarantees. Okay, so no governments are backing it. Technically, it's like the dollar, where we're just printing it, and everybody trusts us as a country to not print a whole bunch of money. So technically, that's not a big deal, but it's hard to trust Bitcoin because there's nobody involved. There's nobody taking the lead in terms of governments, which normally back the money of a certain country. Okay, so that's an economic issue. And so let's think about this. Let's put our deontology hats on. Let's put our utilitarian hats on. What would Kant say about all this? Is it okay? Should we always want to be private when we spend things, when we spend money? Is it okay to always be private? Is it okay to use cryptocurrency even though there are these issues? Is that all right? And I think Kant would be about individual rights, and he would say yes. Sure, you can always use Bitcoin to take part in your transactions, because at the same time, you should also be paying all of your taxes correctly. That's something that you should also always want to do. You should take part in your society and want to make it better. Okay, so Kant would probably be for individual rights because he doesn't think that people are horrible. It's okay to have another form of money, probably, because it may be useful. Maybe you're traveling outside the country, you don't want to pay a bunch of fees to exchange money. It's probably better sometimes to use Bitcoin for some reasons. And so Kant would probably be about individual rights because he doesn't think that people are bad. Mill, on the other hand, or maybe not on the other hand, what would he say? What would a utilitarian think? Well, we'd look at the benefits. He'd look at the benefits and the risks. Okay, so this really depends. It depends on what you're thinking. Depends on how you measure who is gaining. Okay, from the point of view of a government, potentially. From a government's point of view, it's supposed to be apostrophe, not a comma. This is probably a bad thing. Less tax money, more illicit activity. So that's one way you could spin it, and utilitarians would say, if they have that point of view, that it's a bad thing. You could also think of it as a good thing as well, because it makes people more free to not be tracked. So I guess you can put words in Kant's or Mill's mouth, so it's not a big deal, but this is probably the way we would want to think about them. Okay, let me put this over here. And so that is Bitcoin in a nutshell, and we've talked now about computer science and quite a few other disciplines. Let's just move right into the next topic and get started with that. So that the next topic, you may have heard of it, it is technically computer science in another discipline as well, but it's called game theory. So it's really exciting. Maybe you've heard about this, and maybe you've wanted to know more. So let's talk about it at a very high level again. Hopefully, you will learn a bit how to do business, maybe. So here's my example to motivate game theory. We have two corn producers. Maybe we have Fresno State and like a competing school that also grows corn, like UC Davis or something. All right. We have two corn producers. What price should they sell their goods at? Obviously, they both want to make money. They both want to make the most amount of money. Is that a good thing or a bad thing? We'll find out. But the idea is, well, also you can think of this like, instead of corn, like gas stations, they do this. If one seller sells with a high price, like a lot of money, that would be marked with $3 signs on Yelp, and the other sells low, like $1 sign on Yelp, everybody's going to go to this one, right? Because corn is corn. There's probably not artisanal corn that tastes a whole lot better than cheap corn. Everybody's probably going to go and buy the cheap one. So the idea is that game theory will tell us how the prices will get driven down for this person. Okay? They will have to lower their prices a bit to compete with this seller over here. Okay? So in the end, there's going to be some kind of equilibrium. Okay? So eventually, this person's going to change their price to this, and maybe, like, if this was the only other producer, this person would raise their price a little bit, and so then there will be an equilibrium, okay? From the more expensive producer. And the reason we don't want to let companies or markets have free reign is because it is very, very possible, and this has happened many a time in history, that these tool sellers, they will collude on the price, and they'll be like, oh, you know what? We're the two corn sellers in the land, so we're gonna both have the same price, and it's gonna be super high. Hopefully, if you want corn, you're gonna have to pay the price. And oh man, is that illegal? So we don't like that, and this is why there should be a bit of government control over these things, and there is. Left to their own devices, though, we kind of want game theory to happen. That is, in essence, capitalism. Okay, that's the idea. So game theory, the concept, it was kind of formalized back in the day by a man named John Nash, very, very smart man, and he was the topic of a movie called A Beautiful Mind, if you'd like to watch that. It's a very interesting movie. And, okay, let's get into what game theory really is now then. So how was it formalized? How did John Nash do it? So let's call a game, we're going to have to define it first. A game is, from Wikipedia, a strategic interaction between individuals in situations. So this is very, very vague and can handle many, many concepts. Okay? So from your standard tabletop games to video games to corn producers, a lot of things can fall under this. Oops. A lot of things can fall under this umbrella. Okay? There are generally two types of games. A game can be cooperative, so that people are better off working together and forming groups. And so there will be like strength in numbers. If a bunch of groups come together, suddenly they have more combined power and they gain more as a unit. This is like a society, right? This is how like countries are formed and societies are formed. It's a cooperative game to want to be in a country together, I guess. And they can also be non-cooperative, and we'll talk about some of those, where players can't form alliances, And if they ever end up working together, it's because they are threatened, okay? And they're trying to do the best for themselves, and maybe if collaboration ever happens, it's because they are scared otherwise, okay? Which is fun to think about. And yeah, so I guess cooperative game theory, it's about things being fair, like a bunch of people coming together to make something good happen. And then non-cooperative game theory is about winning, like you want the best thing for you. That's the idea. Okay, so that is all these definitions in a nutshell. And game theory is used in many, many fields. Probably the one that it's most famously used in is economics. So if you ever want to study that, maybe that's your major, this might be something that you'll take a class in one day. So it's used in many other fields as well, including computer science. And yeah, I think it's a good all-around topic, and it will be used in many places, so it's a good thing to explain. And people, like in computer science itself, or in other fields, they hire computer scientists. People spend a whole lot of money, and they write a lot of software to solve for optimal strategies in some cases. Like you have all of these companies who are trying to trade stocks very, very quickly, right? Game theory is going to help them discover like what to do in what order. Okay, so the first thing that I want to talk about as a good example is like this quintessential one. It is a non-cooperative game. It is called The Prisoner's Dilemma. Okay, and some people like to put the apostrophe right here, but I disagree with that. There are two prisoners, is plural. Okay, so here is the game. Two prisoners, they are put into separate interrogation rooms, and they are given the following options. Okay, here is the first option, like outcome 1. There are 4 possibilities. Okay, prisoner A, if prisoner A confesses, so they're both given these same outcomes, like one is prisoner A, the other is prisoner B. It doesn't really matter. So option 1, if prisoner A confesses to the crime, because they were both caught together potentially, that person will get 0 years in prison. Okay, they'll walk away free if prisoner B doesn't also confess. Okay, if one confesses but the other does not, that person who confessed gets 0 years, the other person gets 10 years. Ooh, that's unfortunate. That's tricky. This is why this is a non-cooperative game, you see. Okay, if prisoner A doesn't confess, but prisoner B does, then the opposite is true. Prisoner B gets to walk away. Prisoner A gets stuck in prison for 10 years. Outcome 3, they both confess. Each of them, in that case, they get only 5 years in prison. Okay? So, not horrible, but not great. And if this were a cooperative game, which hint hint it's not, they would want to go for outcome 4. Because if they just kept their mouths shut, they would both walk away without anything. Okay? They would both get 0 years in prison. So what should they do? What is going to happen? What is the optimal outcome? For some definition of the word optimal. So what's actually going to happen? And so the idea is, let's make our grid of options. Boop. So here it is. We have 4 outcomes, whether or not prisoner A, like here's prisoner A, here's prisoner B. Prisoner A can confess or not confess, and so can prisoner B. So here are the outcomes for, let's see, A and B in each case. And this will be helpful on the next slide. So these are all the outcomes just in a diagrammatic form. So if they both confess, they get 5 years. If A does not confess but B confesses, A gets 10 years. and B gets 0 years, so this is the opposite there. If B confesses, or B does not confess, they get 10 years if A confesses. There we go, and A will walk away. And if they both don't confess, they both kept their mouth shut, they will get 0 years in prison. Okay, so we're going to solve for the optimal possibility. All right, so I'm going to copy this because I'm going to need it eventually on another slide. So the cool thing that John Nash came up with was this idea of the Nash equilibrium, so an optimal solution to this problem and many other problems that are like it. So a Nash equilibrium is, here's the definition. This is again from Wikipedia, it's a set of strategies, one for each player, that has the property that each player's choice is their best response to the choices of the other players. So they don't know, like A doesn't know what B's gonna do. They don't know, so they have to play it safe. That's the key. They're in separate rooms. Prisoner A doesn't know what prisoner B is going to do. Obviously, they don't trust each other. So they have to play it safe. And the Nash equilibrium is the mathematical formalization of playing it safe. Okay, formalization, I guess I should say. So another more cool example from this YouTube video is that a Nash equilibrium is a law that nobody would want to break, even if there was no punishment for breaking it. Okay? So think of it this way. I'm going to need this again eventually. But first, let's talk about stoplights and why it's a Nash equilibrium to always obey the stoplights. All right? So let's think about this. Here's my stoplight. And you are cars on the highway. Sometimes it's green, sometimes it's red. Okay, why in the world would you want to obey a stoplight? Well, I guess the idea is if nobody obeys the stoplights, you're all going to crash into each other. Okay? And if one person obeys the stoplights, but the other people don't, then they are again getting, they run the risk of getting hurt and, like, never driving again, at the very least. So everybody's going to want to eventually, like, there's an equilibrium case where everybody's going to want to obey stoplights. Because if we just follow those rules, we're all going to be safe and we're not going to get hurt. That is optimal for all of us. So that's essentially the high-level way of thinking about a Nash equilibrium. It's a self-enforcing law. Okay, I should write that. It's a self-enforcing law that you always want to pay attention to, and that's why it has to do with non-cooperative games in a lot of the cases, because they can't actually work together, these players. They feel threatened otherwise. So that's, again, stoplights. We are threatened by other drivers, so we're always going to obey these stoplights. Okay? So, okay, let's do this for the prisoners now. Let's figure out the Nash equilibrium. So for each of the prisoners, what is the average sentence in each outcome? And we don't actually have to do both because they're symmetric, I hope you see. So we can just talk about this from A's point of view or B's point of view. So let's talk about it from A's point of view. Okay? A has two options, okay? Let's actually take this to another slide, in fact. Oop. I guess I can just put that right there. Let's take this to another slide. So, all right, from A's point of view, here's what A could do. So if A confesses, there are two options. I guess I should make this smaller though. Let me use AC for A confesses, okay? And ANC for A does not confess, okay? So in each option, two things could happen for B, okay? So let me draw B in blue. B could confess or B could not confess. I'll say BNC in each case, okay? And so from A's point of view, here's the sentence that A gets. So if A confesses and B confesses, they both get 5 years. If A confesses and B does not confess, they both get how many years? Well, let's go to the table. A confesses, B does not confess. Well, A's getting no time at all. Okay, that's nice. Okay, on the other hand, if A does not confess and B confesses, then let's see here. A does not confess, but B confesses. That means A is getting 10 years. And if A does not confess, but B also does not confess, then, ooh, they're getting 0 years. Okay. So the average sentence, if A does not confess, is 5. Okay, 5 years on average, if A does not confess. And if A confesses, the average sentence is 2.5 years. Do you see that? So the Nash equilibrium, the optimal strategy for each prisoner, this is kind of backwards because it doesn't make sense. This is kind of like a paradox, but it's not. The best case, the optimal strategy for each prisoner, because this is symmetric for B, is to confess, even though if they just both were trustworthy, they would have gotten out free. It makes a whole lot more sense to confess each time. So it's kind of paradoxical. It's weird to think about. That is what a Nash equilibrium is. Okay, so we have just noticed that we've made our own self-enforcing law now. Both prisoners, it would do them well to confess. Okay, so we can assume that that's what's going to happen. And that, I guess, if you watch enough crime shows, that is usually what happens, right? So for the prisoners, what is the average sentence in each outcome? Symmetric for both A and B. So in the average case, it always makes the most sense to confess. This may seem paradoxical. And I guess that's why it's a dilemma. That's why Nash equilibrium was some cool thing that took a while to be invented. Okay? Okay, so that is the Nash equilibrium in a nutshell. We know what's going to happen to the prisoners now. That was a non-cooperative game. Okay, so I think I don't want to get started on anything else because it's already almost the end of class, and so I am going to save cake cutting for next time. That is potentially a cooperative or a non-cooperative game because the internet would not tell me which one it was, but we will start there next time and talk about the optimal strategy for that. So I will see you in the programming lecture.